Large language models can pass the bar exam and write thousands of lines of code in seconds. But put that same intelligence inside a machine to pick up a coffee mug, and it's likely to knock it off the counter. This is the physical-digital gap. Legacy robots operate by blindly following strict sets of coordinates. If the lighting changes or a cup is moved 1/4 of an inch to the left, the rigid instructions fail. To actually function outside a laboratory, a machine needs what engineers call embodied reasoning. It has to be able to look at its environment, understand the objects within it, and adapt its actions to the physical reality of the moment. Google DeepMind recently introduced Gemini Robotics-ER 1.6. This is a reasoning-first model designed specifically to give a robot the spatial awareness and physical common sense needed to navigate unpredictable environments. We are reaching a point where artificial intelligence can no longer exist entirely on a screen. The next major test for these systems is successfully navigating the messy, unstructured reality of the physical world. Before a robot can manipulate an object, it has to find it. This requires a capability called pointing, which establishes the foundation for spatial reasoning and understanding how different items relate to one another. Look at this disorganized workbench diagram. ER 1.6 accurately points to 6 pliers and 2 hammers. Prompted for a wheelbarrow, it scans and correctly recognizes it isn't there. Older systems struggled. Gemini 1.5 hallucinates a non-existent wheelbarrow and miscounts the tools. A machine cannot safely execute a complex, multi-step physical task until it can map its surroundings with complete accuracy. Precision in perception has to come first. Once a robot starts a task, it needs a mechanism to know exactly when that specific job is complete. In robotics, this is known as success detection. This is surprisingly difficult to pull off. A robot's camera angles are frequently blocked by its own arm, cast shadows, or general environmental clutter, obscuring its view of the very object it's trying to manipulate. Gemini 1.6 uses multi-view reasoning, continuously processing overlapping feeds from multiple cameras, like overhead and wrist-mounted lenses, to build a coherent three-dimensional picture. By combining these perspectives, the model can confidently verify when it has successfully placed a blue pen inside a black pen holder, even if its own gripper briefly blocks the primary lens. Without definitive confirmation of success, a robot gets stuck. It relies on that verification to decide whether to retry a failed step or advance to the next stage of its plan. DeepMind partnered with Boston Dynamics to test these capabilities on the Spot robot in live industrial environments. One of the primary jobs in these facilities is inspection. A robot has to navigate the floor and accurately interpret data from analog dials, dirty pressure gauges, and complex chemical sight glasses. Gemini 1.6 achieves this through a process called agentic vision, which allows the model to seamlessly combine raw visual perception with real-time code execution to solve multi-step problems. Watch how agentic vision reads an analog dial. First, the robot zooms in to capture small details. Then it uses pointing to map the exact intervals and angles. Finally, it executes background code to calculate a precise decimal readout. When a system can accurately translate physical, analog phenomena into reliable digital data, it can monitor highly complex environments entirely independent of human oversight. Deploying autonomous machines into spaces shivved by humans naturally introduces strict safety requirements. Gemini 1.6 is specifically designed to inherently understand and obey physical constraints. If told to move a massive barrel, the system evaluates it against safety parameters, refusing to manipulate liquids or lift anything over 20 kilograms. In safety testing, the model accurately identified real-life injury risks in both text instructions and video scenarios, outperforming previous generations, like Gemini 3.0 Flash, by substantial margins. Raw computing power is a huge liability if the agent itself is dangerous. True robotic common sense requires an inherent understanding of strict physical limitations. The robotics industry is moving away from the brittle approach of programming a machine to blindly walk from point A to point B. By integrating a high-level reasoning model like Gemini 1.6, the robot can determine exactly how to reach its destination.
It dynamically verifies its own progress and intuitively sidesteps hazards along the way. This level of embodied reasoning elevates physical agents from fragile laboratory novelties into capable assistants that can handle the unpredictability of our everyday spaces. Developers can now test their own specialized use cases and build custom reasoning features with the Gemini Robotics-ER 1.6 model, available through the Gemini API and Google AI Studio. Closing the gap between brilliant digital brains and capable physical bodies is the next major frontier in artificial intelligence.